Okay, so just to recap our previous video, right, here is the actual graph that we were talking about, and you can see, right, if I look at the curve, e to the x, which is the dark line, and I look at the tangent line that's labeled P1 here, okay, they do act like each other really close to that center point, the point 0, 1. But the further you move away, the worse approximation it is. Okay, so if I want to improve this approximation, you can impose another requirement. You could say that when x equals 0, not only do the values need to agree, not only does the first derivative have to agree, but also the second derivative at 0 has to agree. And if you do that, you get this polynomial, right? We'll talk about where that comes from a little bit in the next slide. Well, you can see if you take a look at this polynomial, this curve, it definitely is a better approximation to the curve e to the x than a straight line. Not really that surprising, right? So if you continue to require that more and more derivatives are the same, right, then you can get the nth degree approximation shown here. Okay, and I think that should look a little bit familiar. There will be a GeoGebra demo after we talk about where this is coming from a little bit. Okay, so Taylor and Maclaurin polynomials, that's what are going to be our focus for this. And so we're going to focus on kind of general, and then we will look at that a little bit more in particular for e to the x. Okay, so in general, okay, a Taylor polynomial looks something like this. Okay, where we have the nth degree Taylor polynomial because the last exponent is going to match that. Okay, so the nth degree because it's going to be an n degree polynomial. It looks like a sub 0 plus a sub 1 times x minus c to the first plus a sub 2 x minus c squared, so on and so forth, till a sub n x minus c to the n. By looking at this, you should be able to tell the center is at c, right? So when x equals c, that would be the center. Okay, now I'm going to take a whole bunch of derivatives of this polynomial. If I take the derivative, a sub 0 is just some number, right? And so that part would disappear. When I take the derivative of a sub 1 times x minus c to the first, I would just get a sub 1 because the derivative of x minus c is just 1. When I take the derivative of a sub 2 times x minus c squared, the 2 is going to come down, so 2a sub 2 times x minus c to the first. Okay, the next one would be 3a sub 3 times x minus c squared. I could do the next one, right? Even though it's not written out, I bet you can make a prediction, right? 4a sub 4 x minus c to the fourth. And then if I thought about doing the last one, it would follow that same pattern. The exponent would come down times the existing coefficient times x minus c to the 1 less power. Okay, so that's what it would look like. If I then take the derivative of the derivative, aka the second derivative, the derivative of a sub 1 again would be 0. The derivative of 2a sub 2 times x minus c to the first would just be 2a sub 2. Okay. The next derivative, when I look at taking the derivative of this term, remember the old power comes down and multiplies by the existing coefficient. So 6a sub 3 times x minus c to the first. Okay, the next one, I forgot to change this exponent. This should have been a 3. My apologies. The next one would be 12a sub 4 times x minus c squared. And the last one would be the n that's already there times the power n minus 1 times a sub n times x minus c to the 1 less power, which would be n minus 2. All right, let's do it again. So much fun, right? Third derivative. Oops, can't talk and write at the same time. 2a sub 2 is just a number. That's gone. The next one's going to be 6a sub 3 times 1, because that's the derivative of x minus c. So that's good. The next one, 12 times 2, so 24a sub 4 times x minus c to the first power. Okay, so we're keeping all of the things that were there before as part of the coefficient, right? And then we're always multiplying by the power that used to be there. And then the power on the x minus c part is going down by 1. Okay, one more time, fourth derivative. Can't stop, won't stop, right? Okay, derivative of that first term is going to be 0. I'm going to get 24a sub 4 times x minus c. Derivative would be 1, so I'm good. Okay, and then it would be n times n minus 1 times n minus 2 times n minus 3 a sub n times x minus c to the n minus 4. And I could keep going, right, as long as I want to. I want to start talking about how to get the actual coefficients. Okay, so how do I get the coefficients that I need to make this match, right? Like, how do they know how to figure out what they should be for that e to the x curve? Okay, so one thing I can do is I could plug in the c value for the center. So if I go back up here, right, and instead of x, I put a c, that means replacing all of these with c's, right? I think you can see what's going to happen, because this part is going to be 0. That's going to go away, right? This part would be 0, so that part would go away, 0. All of these turn out to be 0, and so the only thing you'd be left with if you plugged in 0 to the polynomial would be that first leading coefficient that didn't have any x's at all, the a sub 0. Okay, and I'm going to do that pretty much with all of them up there. Okay, and then the next one, in the first derivative, if I plug in the center of 0, right, take a look up here, this part would go away, this part would go away, this part would go away, this part would go away. I'd just be left with a sub 1. Okay. Second derivative, if I plug in 0, right, all of the terms are going to go away except for this first term because it didn't have any x's in it at all. And so this will be 2 a sub 2. You might be tempted to say, I get the pattern, right? It's just the next one, when I do the third derivative, if I put in c, I'm going to get 3 a sub 3. I have this figured out. Ruh-roh, not really true though. If I look at that third derivative, that part goes away, that part goes away, but my leading, or my only part that would be left is not 3 a sub 3, it is 6 a sub 3. And so you might be kind of wondering, right? And if I do the fourth derivative and I plug in c, okay, I do not get 4 a sub 4, I get 24 a sub 4. So hopefully you're thinking about the pattern. Now, we did not do the fifth derivative, but I think some of you probably can take a guess, right? What is going to be the number in front of a sub 5? Take a second and guess. Okay, I'm going to tell you, now that you've taken your second, it's 120. And what I want you to start thinking about is, do I know these numbers? Okay, because it's definitely not what we thought it was going to be, and so maybe we need to make some guesses. I think specifically thinking about this number in relation to this, right? This number in relation to this number in relation to this. My hope is you recognize those numbers. This is actually 5 factorial a sub 5. This is actually 4 factorial a sub 4. This is actually 3 factorial a sub 3, and really 2 factorial is 2, so this is 2 factorial a sub 2. And here there is a 1. Well, 1 factorial is 1. And there's a 1 here, and you might be worried about that, but guess what? Remember, 0 factorial is also 1. And so here is a way to figure out, right, all of these coefficients that I need. Well, what if I actually solve these equations for the coefficients? And that's what we're about to do right now. So let's solve for the coefficients. So the last one was kind of how are we building them, and now we're going to get those coefficients alone. Well, a sub 0 then would be p of c divided by 0 factorial, but that's just dividing by 1, so we could just say that's the same thing as that polynomial evaluated at c. A sub 1 is the first derivative, evaluate c divided by 1 factorial. Well, again, not that exciting because 1 factorial is just 1, but it helps us to see the pattern because a sub 2 is p double prime, evaluate c divided by 2 factorial. And a sub 3, if I solve this equation for a sub 3, okay, is p triple prime, evaluated at c divided by 3 factorial. And we could keep going on and on and on, right? The point is to find a pattern. How do I come up with the nth coefficient? The nth coefficient would be the nth derivative evaluated at c divided by n factorial, right? And this is the key to being able to come up with the coefficients in these approximating polynomials.